Okay. The model's titled Membrane Potential. It's an electrostatic simulation. And let's look at the geometry here. Now, the previous problem had rotational symmetry about the z-axis. We could have done that just as well in this problem. However, I've done this in XY symmetry. That is, that the plane of the membrane here, the central region, would be extending out. And this has a rectangular symmetry. It's not rotated about the z-axis here. Once again, the membrane thickness is about 7 nanometers. And we'll look at the block labels. This is the extracellular region. It has a permittivity close to water. And I've chosen a charge density of 30,000 coulombs per cubic meter. That may seem like a very large number. And this really refers to the charge density that's immediately adjacent to the cell membrane. In the intracellular region, I've chosen a permittivity 50 and an opposite charge density here. Now, living cells have a charge of about 10 to the negative 15 coulombs with a diameter. A yeast cell has a diameter of about 5.7 microns. So the average charge density throughout the cell will be roughly 17 coulombs per cubic meter. However, we will have increased ionic concentrations close to the membrane because the cell is negatively charged and it's going to attract positive ions into solution. Okay. Now, as far as the edge labels, this is the bottom edge where I have 0 normal electric field. All we have is tangential electric field. And on the top boundary, this is not the top boundary, but the boundary in between directly bisecting the membrane, I've given it a 0 voltage. And we have to have at least one Dirichlet condition in the model. That means we need at least one node has to have a fixed potential. Otherwise, that's arbitrary, and we need to have at least one. On the top boundary, I have, once again, 0 normal electric field, which I've specified by this condition here. Okay. And if we look at the, we solved the problem. It's already been solved, but we'll go ahead and solve it again. Okay, so this is a plot of the equipotential lines along the cell. If I want to look at the electric field, I can look at vectors of the electric field here. And we can see that the electric field is much stronger inside of the membrane here than outside. I can make a contour plot spanning the membrane here, and I go to my contour tool, and I'm just going to specify a contour that spans the membrane here. And so I've specified my contour, and then I go to XY plot, and the first thing it'll show me is the potential. Notice that the potential is continuous. However, the derivative is not continuous at the interior and the exterior of the cell here. This would be the interior. This is right at the edge of the plasma membrane. And I've chosen those charge densities so that we have a membrane potential, or a delta V, of 100 millivolts spanning the membrane. And I want to look at the field strength. Okay, you can see that the field strength is discontinuous. And it's on the order of 10 to the 7 volts per meter here inside of the membrane, which is accurate. That this would be the true field inside of the membrane. Now, because we have such a large electric field inside of the membrane, any ions or charges inside of the membrane are going to be affected by this. And I wanted to do a simulation that models the presence of charges inside of the membrane, and these objects or often proteins, enzymes are used for transporting ions from one side of the membrane to the other, and they can have electric charge. This just shows a schematic of the lipid bilayer with the hydrophobic tails facing each other and the phospholipid heads, and this represents two charges inside of the membrane. And I'm going to do another electrostatic calculation in QuickField. So let's put this problem up. This is membrane charges. And this is the model. Once again, I've created this model in XY symmetry. So this does not have rotational symmetry about this axis. And this would be a cylindrical membrane that's coming out of the plane of the desktop here, similar to an axonal membrane. And I'm going to zoom in here, and I've got I've specified two charges. And if we look at the block labels, this is the membrane, and I've just embedded in a water region for now, which permittivity of 78. On the boundary of the model, I've just assigned 0 potential. However, we do have a couple vertices, a plus Q and a minus Q here, and I've given it very small charges. In fact, the electronic charge. Now, let's go ahead and solve the problem. It's already been solved. Something like 50,000 nodes, which is maybe a little excessive for this problem. Okay. So the field is a dipole field. However, the dipole field is distorted by the membrane here because it has a different dielectric constant. The dielectric constant of the membrane is about roughly 10, whereas the dielectric constant, the relative dielectric constant in the exterior region is close to that of water. Now, in the previous problem we showed that there was a very strong electric field across the membrane, and that electric field will exert forces and affect the conformation of any membrane proteins or enzymes of finite extent here.